Hello there, and welcome to Simple Sleepy Science Channel. There are questions that keep scientists awake at night, not because they're worried, but because they're wonderful. Questions without answers. Mysteries that sit at the edge of everything we know. Tonight, we're going to explore 100 of them together. Not to solve them, but to rest in their beauty. To let wonder wash over us like a gentle tide. Tonight, we drift into something special. A journey through the unknown. Through questions that science is still trying to answer. And here's what makes this beautiful. We don't need the answers to find peace. Sometimes the questions themselves are enough. This is a place for calm curiosity, a place where mystery meets rest, where wonder helps us let go. So, get comfortable. Settle into your space. Let your body sink a little deeper. We're about to explore the most profound mysteries in science, and we're going to do it gently. One question at a time, one breath at a time. Before we begin, if these quiet journeys bring you calm, if you enjoy drifting off to the mysteries of science, consider subscribing to join fellow science lovers here, and leave a comment telling us where you're watching from and what time it is there. We love knowing you're out there, somewhere in the world, wondering with us. Now, let's start with the mystery closest to home, the one you're experiencing right now. What is consciousness? You're aware. You're reading these words or hearing this voice. You're thinking, feeling, experiencing this moment. But what is that? What is this thing called awareness? Scientists call it the hard problem of consciousness. And it's hard because we can explain a lot about the brain. We can map it, measure it, watch it light up when you think or feel. But we can't explain why any of that creates experience. Why you feel like you. Why there's something it's like to be you. Your brain has about 86 billion neurons. They talk to each other through tiny electric signals, chemicals flowing across gaps smaller than you can imagine. And somehow, from all that chemistry and electricity, you emerge. A person with thoughts, with feelings, with a sense of self. But how? Where in all those neurons does consciousness live? Is it in one place or everywhere? Does it happen all at once or build up slowly? We don't know. Some scientists think consciousness is what happens when information gets processed in certain ways. Others think it might be something fundamental to the universe itself, like gravity or time. Some wonder if we'll ever really understand it, because we'd need to be conscious to study consciousness. Like an eye trying to see itself. And here's another mystery that lives right next to consciousness. Why do we dream? Every night, you slip into another world. A world your brain creates from memory and imagination. Sometimes dreams make sense. Often they don't. You fly, you fall. You meet people who aren't real or who left long ago. Time bends. Physics breaks. And when you wake up, most of it fades like fog in the morning sun. Scientists know that dreaming happens mostly during REM sleep. That's when your eyes move rapidly under your eyelids and your brain becomes almost as active as when you're awake. But why? What purpose does dreaming serve? Maybe dreams help us process emotions. Maybe they sort through memories, deciding what to keep and what to let go. Maybe they let us practice for threats we might face, running simulations while we're safe in bed. Or maybe dreams are just noise, random firings of neurons that your brain tries to make sense of. We still don't know. And then there's dark matter, the invisible mystery that holds galaxies together. Scientists know it's there because of how galaxies spin and how light bends around them. But what is it made of? We can't see it, can't touch it, can't detect it directly. Yet it makes up most of the matter in the universe. These three mysteries, consciousness, dreams, and dark matter, show us something beautiful. They show us that for all we've learned, the universe still has secrets. And that's okay. That's more than okay. That's wonderful. Because mystery invites us to stay curious, to keep looking, to rest in not knowing while we appreciate what we do know. From the inner space of your mind to the outer space between galaxies, questions wait, and we're going to visit them one by one, letting each mystery become a soft place to land as we drift towards sleep. Your brain weighs about 3 pounds. It's soft, wrinkled, and uses less power than a light bulb. Yet it creates everything you experience, every thought, every memory, every feeling, and we still don't understand how. Let's stay here for a moment, inside your mind, where some of science's deepest mysteries live. We talked about consciousness, that strange fact of being aware. But here's what makes it even more puzzling. Your brain doesn't experience the world in real time. Everything you see, hear, and feel happened a split second ago. Your brain takes time to process signals from your senses, so it predicts what's happening now based on what just happened. You live in your brain's best guess about reality. And that leads us to another mystery. What causes intuition? You know that feeling, that sudden knowing without knowing why you know. You meet someone and instantly sense you can trust them. Or you can't. You walk into a room and feel something's wrong. Scientists call these gut feelings, and they're real. But where do they come from? Maybe your brain notices patterns you're not consciously aware of. Tiny details, subtle cues, and it sends you a feeling instead of a thought. Or maybe intuition comes from deeper, older parts of your brain, parts that evolved long before language. We're still figuring it out. Here's another one. Why do we yawn? You know what a yawn feels like. That deep, slow breath. Your mouth opens wide. Your eyes might water. And here's the strange part. Yawns are contagious. You see someone yawn, and suddenly you need to yawn too. Even reading about yawning can trigger one. Scientists used to think yawning brings more oxygen to your brain, but that's not it. Now some think it cools your brain down, like a radiator for your mind. Others believe it's about staying alert, a way to wake up your nervous system. But we don't really know, and we definitely don't know why yawns spread from person to person like a gentle wave. Then there's memory. You can remember your first day of school, the smell of rain, a song from years ago, but you can't remember what you had for lunch last Tuesday. Why? Your brain doesn't record everything like a camera. It rebuilds memories each time you recall them. And every time you remember something, you change it a little. Add details, remove others. Mix in feelings from now with feelings from then. Scientists know where memories form. there's a seahorse-shaped part of your brain called the hippocampus. Damage it, and you can't make new memories. But we don't know exactly how memories get stored. How does a thought become something you can keep? How does your brain decide what matters enough to remember? And here's the mystery that might matter most right now. How does anesthesia work? Doctors put people to sleep for surgery every single day. They use drugs that turn off consciousness, like flipping a switch. You're awake, then you're not, then you're awake again. And you don't dream. You don't experience time passing. You just disappear for a while. But we don't know why these drugs work. We know they affect your brain. We can see that, but we can't explain how they erase consciousness. What are they turning off? Where does your awareness go? It's one of medicine's most useful mysteries. Your mind holds these questions, and so many parts. Why do some people hear colors or see sounds? What causes déjà vu, that eerie sense you've lived this exact moment before? How do you recognize a face in a crowd instantly? Without thinking, each mystery connects to the next. Consciousness leads to intuition. Intuition touches memory. Memory shapes dreams. And all of it happens in that 3-pound universe inside your skull. But your brain doesn't work alone. It sits inside a body that has mysteries of its own. A body that needs sleep, though we don't fully know why. A body that urges, though we can't stop it. A body that sometimes heals itself with belief alone. Let's look at those mysteries next. Your body speaks a language you don't fully understand. It sends signals, releases chemicals, responds to the world in ways that science is still decoding. Take sleep. You're probably getting drowsy right now. Your eyelids feel heavy. Your thoughts drift. Your body knows it needs rest. But why? Every animal sleeps in some form. Birds do it. Fish do it. Even fruit flies sleep. It's universal. It's essential. Go without sleep long enough and you'll die. But we still don't know exactly why we need it. Sleep isn't rest, in the way sitting down is rest. Your brain stays busy all night. It consolidates memories, clears out waste, processes emotions. Your body repairs tissue, balances hormones, recharges your immune system. But why can't we do these things while awake? Why must we lose consciousness for hours every day? The full answer remains hidden. And here's another mystery your body carries. Why do we age? You're older now than when you started reading this. Your cells are dividing. Your DNA is copying itself. And each time it copies, tiny errors creep in. Telomeres, the protective caps on your chromosomes, get shorter. Free radicals damage your cells. Proteins misfold. Slowly, things break down. But why? From an evolutionary view, aging seems wasteful. If bodies could repair themselves perfectly, we could live longer, reproduce more, pass on more genes. Yet every living thing ages and dies. Some scientists think aging is programmed, a biological clock we can't turn off. Others think it's just accumulated damage, like a car that eventually wears out. We're trying to understand which one is true, or if maybe both are. Then there's the placebo effect. Give someone a sugar pill and tell them it's medicine. Sometimes they get better, not just in their mind, but in measurable, physical ways. Pain decreases, inflammation goes down, symptoms improve. Your brain can change your body through belief alone. But how? What pathway connects a thought to actual healing? We know it happens. We use it in every medical trial. But the mechanism, the exact way belief becomes biology, remains unclear. Why do you get goosebumps when you're cold or scared? Those tiny bumps on your skin come from muscles pulling on your hair follicles. In animals with thick fur, this fluffs them up for warmth or makes them look bigger to threats. But humans barely have fur anymore. So why do we still get goosebumps? It's a leftover from our evolutionary past, but we don't know if it serves any purpose now. What triggers hiccups? Your diaphragm, the muscle that helps you breathe, suddenly spasms. You gulp air. Your vocal cords snap shut. That's the hic sound. But why does this happen? Hiccups serve no obvious purpose. Some think they're another evolutionary leftover, maybe from when our ancestors were transitioning from water to land. Others think they help babies coordinate sucking and breathing. Nobody's certain. And why do we blush? Blood rushes to your face when you're embarrassed. Your cheeks turn red. Everyone can see it, which makes the embarrassment worse. From a survival standpoint, this seems terrible. Why would evolution create a signal that broadcasts our mistakes? Some scientists think blushing is a non-verbal apology, a way to show others we know we messed up. But that's just a theory. Your body keeps score in ways you can't see. It remembers trauma in your muscles, stores stress in your stomach, expresses emotions through your skin. The connection between mind and body runs deeper than we understand. These mysteries live inside you, not out in space or deep in the ocean, but right here, in your breath, in your heartbeat, in the way your body knows what to do even when you don't. And all of this, all these processes and mysteries, trace back to something even more profound. The question of how life itself began. About 4 billion years ago, Earth was nothing like it is now. No trees, no grass, no animals, just rock and water and chemicals. And then something happened. Something that has only happened once, as far as we know. Life began, but how? This is one of the biggest questions in science. Not just because we don't know the answer, but because we might never know. We can't go back in time. We can't watch it happen. We can only guess based on clues left behind in ancient rocks and the chemistry of living things today. Here's what we think we know. Early Earth had the right ingredients: water, carbon, nitrogen, phosphorus, energy from lightning and volcanic vents. These chemicals mixed together in warm pools or deep ocean vents. And somehow they organized themselves into something more. Something that could copy itself. Something alive. But that word, somehow, hides the real mystery. Life needs information. Instructions for building itself. Today, that information lives in DNA. DNA is like a twisted ladder made of chemical letters. 4 letters, A, unanswered, arranged in sequences that tell cells what to do. It's elegant, it's efficient, it's incredibly complex. Too complex to be first. So, scientists think something simpler came before DNA. Probably RNA. RNA is like DNA's single-stranded cousin. It can store information and also do chemical work. Maybe RNA was the first molecule that could copy itself, the first spark of life. But here's the puzzle. To copy itself, RNA needs proteins. And to make proteins, you need RNA. It's a chicken and egg problem. Which came first? We don't know. Maybe they evolved together. Maybe something even simpler came before both of them. Maybe life started multiple times before it finally stuck. The origin is hidden in deep time, buried under billions of years of change. And then there's the question of what life actually is. How do you define it? Living things grow. They reproduce. They respond to their environment. They maintain themselves despite chaos around them. But is that enough? Fire grows and responds to its environment too. Crystals reproduce their patterns. Are they alive? Most scientists say no. Life needs metabolism, the ability to take in energy and use it. Life needs evolution, the ability to change over generations. But even these definitions get fuzzy at the edges. What about viruses? They have genes, they reproduce, they evolve, but they can't do any of this alone. They need to hijack living cells. So, are viruses alive, or just very complicated chemicals? Scientists still argue about this. Could life start again? Right now, on Earth? Probably not. Early Earth was different. The atmosphere had no oxygen. That meant no ozone layer. More ultraviolet light reached the surface, providing energy. The ocean chemistry was different. And most importantly, there was no life yet to eat any new life trying to form. Today, if simple organic molecules started organizing into something alive, bacteria would consume them before they got very far. Life now prevents new life from beginning. We had our chance, and we took it. But maybe life started somewhere else. Maybe it's starting right now on another world, on a moon orbiting a distant planet, in a subsurface ocean warmed by tidal forces, in a cloud of chemicals around a young star. The question isn't just how life began here. It's whether life is rare or common, special or inevitable, one miracle or many. Once life started, it changed, it adapted, it spread, it became more complex. And that process, evolution, has mysteries of its own. Life didn't stay simple. It exploded into forms we can barely imagine. And some of those forms left questions that still puzzle scientists today. Why did dinosaurs grow so enormous? A blue whale is the largest animal alive today, but some dinosaurs were just as big, and they lived on land where gravity pulls harder. Argentinosaurus might have weighed 100 tons, as much as 20 elephants. How did their bones support that weight? How did their hearts pump blood up those long necks? How did they eat enough to fuel those massive bodies? Part of the answer is in their bones. Dinosaur bones were hollow, filled with air sacs like birds have. This made them lighter, but still strong. And dinosaurs were more efficient than mammals. They needed less food for their size. But we still don't know why evolution pushed them to such extremes. Why bigger kept being better for so long. Then, about 66 million years ago, an asteroid hit Earth. The dinosaurs vanished. Almost everything vanished. But life came back, and when it did, something strange happened. About 540 million years ago, life suddenly diversified in ways it never had before. Scientists call this the Cambrian explosion. Within just a few million years, most major animal groups appeared. Animals with eyes, with shells, with jointed legs. The fossil record goes from simple to complex almost overnight in geological terms. But why then? What triggered this burst of creativity? Maybe oxygen levels in the ocean finally got high enough to support complex bodies. Maybe predators evolved, forcing prey to develop defenses, which forced predators to get better in an arms race of evolution. Maybe it was eyes. Once one animal could see, everyone needed to either hide, defend themselves, or see too. We have theories, but the full picture stays unclear. And here's another puzzle. Flight evolved at least 4 separate times. Insects developed it. Pterosaurs had it. Birds have it. Bats have it. Each group invented flight independently, using completely different body plans. That seems like it should be incredibly hard. Flight requires hollow bones, powerful muscles, efficient lungs, and perfect balance. Yet evolution found the solution again and again. Why is flight so achievable? What makes it worth the enormous cost of developing it? There are about 400,000 beetle species on Earth. That's more than any other type of animal. 1 in 4 animal species is a beetle. Why? Some say it's because beetles have armor, those hard wing covers that protect them. Others think it's because they can eat almost anything. Some beetles eat plants. Some eat meat. Some eat dung. Some eat other beetles. This flexibility might have let them fill countless different roles. But we're not certain why beetles specifically became so successful. Eyes are another mystery. They evolved separately dozens of times. Octopus eyes look almost identical to human eyes, but they evolved completely independently. We don't share an ancestor with eyes. Somehow, evolution discovered the same solution twice. This suggests eyes are almost inevitable. If you're going to sense light, there are only so many good ways to do it. A lens, a light-sensitive layer, a dark chamber. The physics push toward the same design. But what drives extinction? Not the asteroid kind, the slow kind, background extinction, where species disappear one by one over millions of years. Why do some survive and others vanish? Is it luck, timing, flexibility? We see the patterns, but not always the reasons. Evolution works through endless trial and error. It builds on what came before. And it all happens on a planet that's been changing since the beginning. The ground beneath you feels solid, permanent, but Earth is restless. It moves, it changes, and at its heart sit mysteries we've never seen. What's at the center of the Earth? You're standing on a crust that's only about 20 miles thick. Below that is the mantle, hot rock that flows like thick honey over millions of years. Below that is the outer core, liquid iron and nickel, spinning and creating Earth's magnetic field. And at the very center sits the inner core, a solid ball of iron about as hot as the surface of the sun. We've never been there. The deepest hole ever drilled only went down about 7.5 miles. The pressure and heat deeper down would melt any drill we could make. So how do we know what's down there? Earthquakes. When an earthquake happens, it sends waves through the entire planet. Scientists measure how those waves bend and slow down as they pass through different materials. It's like using sound to see inside something you can't open. And from those waves, we've built a picture of Earth's interior. But here's what we don't know. The inner core seems to be rotating slightly faster than the rest of the planet. Why? And there might be another layer inside the inner core, with crystals aligned differently. We're still figuring out the structure of our own planet's heart. How did the moon form? Look up at night and you'll see it. Earth's companion. Our moon is huge compared to Earth, much bigger relative to its planet than most moons in the solar system, and it's moving away from us, about 1.5 inches every year. The leading theory is called the giant impact hypothesis. About 4.5 billion years ago, a Mars-sized object crashed into early Earth. The collision was so violent it vaporized rock. Debris sprayed into orbit, and from that debris, the moon formed. We're fairly sure this happened. Moon rocks brought back by astronauts match Earth's composition, but the details remain fuzzy. How big was the impactor exactly? What angle did it hit? How quickly did the moon come together? Each answer leads to more questions. And why does Earth have plate tectonics? Earth's crust is broken into massive pieces that drift on the mantle below. They spread apart at ocean ridges. They collide and push up mountains. They slide past each other, causing earthquakes. This movement recycles the crust, pulls carbon into the mantle, and might be essential for life. But Earth is the only planet we know that does this. Venus doesn't have plate tectonics. Mars doesn't. Why are we special? Maybe it's our water. Water lubricates the boundary between crust and mantle, helping plates slide. Maybe it's our moon. The moon's gravity creates tides that might have helped get plate tectonics started. Maybe it's our size, our distance from the sun, or pure chance. We're still working it out. What causes ice ages? Earth goes through cycles where ice sheets grow and cover huge areas, then retreat. These cycles follow patterns related to Earth's orbit and tilt. But the timing doesn't always match perfectly. Other factors play a role. Ocean currents, volcanic eruptions, even the arrangement of continents. We understand pieces, but not the whole system. How did Earth get its water? Did it come from comets and asteroids after Earth formed? Or was some water already here, trapped in the rocks that built our planet? Different sources have different chemical signatures. The water in Earth's oceans matches asteroids better than comets, but not perfectly. The full story of where our water came from stays partially hidden. And why does Earth have a magnetic field that protects us from solar radiation while Mars lost its field billions of years ago? Our planet holds mysteries in its depths and in its dance with the moon above. Earth's water covers most of the planet, and beneath the surface lies a world we've barely explored. We've mapped more of Mars than we have of our own ocean floor. The deepest part of the ocean is the Mariana Trench. It goes down almost 7 miles. If you put Mount Everest at the bottom, its peak would still be underwater. The pressure there is immense. more than 1,000 times the pressure at the surface, enough to crush most submarines like tin cans. Yet life exists there, fish with bodies built to withstand the crushing weight, translucent creatures that glow in the darkness, amphipods the size of your hand. But we don't know everything that lives down there. Every deep-sea expedition finds species we've never seen before. What lives in the deepest parts? We've sent cameras and robots. We've collected samples. But these are brief visits to a vast frontier. Most of the deep ocean remains unexplored. There could be entire ecosystems we haven't discovered yet. How many species live in the sea? On land, we've catalogued about 1.5 million species. In the ocean, we've identified about 200,000. But scientists estimate there might be up to 2 million more. Maybe 10 times what we know about. The ocean hides its diversity well. Some of that mystery glows. Bioluminescence, the ability to make light from chemical reactions inside the body. About 80% of deep-sea creatures can do this. They use it to hunt, to hide, to communicate, to attract mates. But what causes it? We know the chemistry. A molecule called luciferin reacts with oxygen, helped by an enzyme. This creates light with almost no heat. It's incredibly efficient. But we don't fully understand why so many ocean creatures evolved this ability, or how they control it so precisely. Whales sing. Their songs travel hundreds of miles underwater. Each population has its own dialect. The songs change over time, like musical trends passing through whale culture. Humpback whales create complex patterns of moans and cries that can last half an hour. Then they repeat the whole sequence. Why? We think it's about mating. Males sing to attract females or compete with other males. But we're not certain. The songs are too complex for just that. Maybe they navigate by them. Maybe they share information about food. Maybe there's meaning in those songs we can't decode. The Mariana Trench holds Arthur's secret. In parts of it, the water is actually less salty than normal seawater. Scientists think this is because chemical reactions in the rocks are creating fresh water. Deep beneath the ocean floor, water seeps into cracks, gets heated by Earth's interior, reacts with minerals, and rises back up, changed. These hydrothermal vents create whole ecosystems based not on sunlight, but on chemicals from Earth itself. How do creatures survive the pressure? At those depths, water wants to flood into cells and crush them. Deep-sea fish solve this with special proteins and molecules that counteract the pressure. Their cells are filled with compounds that stabilize them. But we're still learning exactly how this works at the molecular level. Some deep-sea creatures live longer than we ever expected. Greenland sharks might live for 400 years or more. Some deep-sea coral colonies are thousands of years old. In the cold, dark depths, metabolism slows down. Life takes us its time, though ocean keeps its secrets. But above the water, in the air we breathe, more mysteries swirl. The air around you is never still. It rises and falls. It swirls and flows. It carries water from the ocean to the sky and back again. And in all that movement, mysteries hide. How exactly do clouds form? You've seen them your whole life. White puffs on summer days, grey blankets before rain. towering thunderheads reaching miles into the sky. But the process of making a cloud is more complicated than it seems. Water vapor needs something to condense onto: a speck of dust, a grain of salt, a particle of pollution. These are called cloud condensation nuclei. Without them, water vapor can stay in the air even when conditions are right for clouds. The vapor becomes supercooled, liquid droplets below freezing that haven't turned to ice yet. We understand the basics. Warm air rises, cools, and can't hold as much water, so clouds form. But predicting exactly when and where clouds will appear is still difficult. Tiny changes in temperature or the number of particles in the air can completely change cloud behavior. And clouds affect climate in ways we're still measuring. Lightning is even stranger. During a thunderstorm, ice particles in clouds collide. These collisions somehow create electric charge. Positive charge accumulates at the top of the cloud. Negative charge builds up at the bottom. When the difference gets big enough, electricity jumps from cloud to ground. But we don't know exactly how those collisions create charge. The ice crystal mechanism isn't fully understood, and lightning moves in ways that still surprise us. It can travel sideways for miles. It can strike from blue sky, and sometimes it creates something truly bizarre. Ball lightning, glowing spheres that float through the air. They pass through walls. They last for seconds or minutes. People have reported them for centuries, but scientists rarely see them. We don't know what they're made of or how they form. Some think they're plasma held together by magnetic fields. Others think they're chemical reactions or optical illusions. Ball lightning exists in that strange space between proven and explained. Can we predict earthquakes? We can measure them when they happen. We can map fault lines where they're likely to occur. But predicting the exact time an earthquake will strike remains impossible. Earthquakes happen when stress builds up along faults where tectonic plates meet. The rocks stick together for years or centuries. Then suddenly they slip, releasing energy in seconds. But we can't measure the stress deep underground well enough to know when that slip will happen. Earthquakes give almost no warning. Some animals seem to sense them coming. Minutes or hours before the shaking starts, animals behave strangely. Dogs bark, birds fly away, fish swim erratically. Maybe they feel early vibrations humans can't detect. Maybe they sense changes in the Earth's magnetic field. We don't know for sure. The jet stream, that river of fast wind high in the atmosphere, drives weather patterns across continents. It separates cold polar air from warmer air to the south. But it doesn't flow straight. It meanders in waves. And lately, those waves seem to be getting bigger and moving slower. This might be causing more extreme weather. Heat waves that last longer. Cold snaps that dig deeper south. But we're still figuring out if this is a trend or natural variation. Tornadoes spin faster than almost any other wind on Earth. Inside the strongest ones, wind speeds might reach 300 miles per hour. We know warm, humid air meeting cold, dry air creates the conditions for them. But we can't predict exactly which thunderstorms will drop a tornado. The final trigger stays hidden in the chaos of swirling air. These mysteries in our atmosphere connect to something bigger. They connect to the star that warms our world. The sun rises every morning. It warms your skin. It lights the day. It's been doing this for nearly 5 billion years, and we still don't understand parts of it. At the center of the sun, hydrogen atoms fuse into helium. This releases energy. Huge amounts of energy. That energy takes about 100,000 years to work its way from the core to the surface, bouncing between particles in a slow, random walk. Then it flies through space as light, reaching Earth in just 8 minutes. The surface of the sun is about 10,000 degrees, hot enough to vaporize anything. But above the surface sits a layer called the corona. You can see it during a solar eclipse, a glowing halo of light around the dark circle of the moon. And here's the mystery. The corona is millions of degrees hotter than the surface below it. That shouldn't happen. Heat doesn't flow from cool to hot on its own. That's like water flowing uphill. So, what heats the corona? Scientists have theories. Maybe magnetic fields rising from below carry energy up. Maybe waves traveling through the sun's atmosphere heat it. Maybe millions of tiny explosions called nanoflares do it. We've sent spacecraft closer to the sun than ever before to study this. We've measured the magnetic fields and the particles flying off the sun. But we don't have the complete answer yet. The sun's activity follows a cycle. About every 11 years, the number of sunspots peaks. Sunspots are cooler, darker patches on the sun's surface, where magnetic fields poke through. When there are lots of sunspots, the sun is more active. More solar flares, more eruptions of particles into space. Then the sunspots fade, and the sun calms down. But why 11 years? Why does this cycle happen at all? And why isn't it perfectly regular? Some cycles are shorter, some longer. Some have more sunspots than others. The pattern comes from the sun's magnetic field, which flips north to south every 11 years. But we don't fully understand what drives this magnetic dance. Solar flares are sudden bursts of energy from the sun's surface. In minutes, they release as much energy as billions of nuclear bombs. They send X-rays and ultraviolet light flying into space. They can disrupt radio communications on Earth. They can damage satellites. We can see them happen. We can measure them. But predicting exactly when and where a flare will erupt remains hard. We watch sunspots and magnetic field tangles where flares are likely. But the trigger, the final moment when everything lets go, stays uncertain. What's inside the sun's core? We've never seen it directly. We can't send anything there. The pressure and temperature would destroy it instantly. So, we use helioseismology. We watch how waves move through the sun, just like we study Earth's interior with earthquake waves. These waves tell us about density and temperature and composition. But there's always uncertainty. Models predict the core temperature is about 27 million degrees. They predict fusion rates and particle flows. But small changes in those predictions matter. They affect how we understand energy generation and the sun's future. Sunspots themselves are mysteries in detail. We know magnetic fields cause them, but why do they appear in pairs? Why do they form at certain latitudes? Why does their number vary so much? Each answer reveals new questions about the magnetic processes happening beneath the surface. The sun is our closest star, And beyond it, in our solar system, worlds orbit with secrets of their own. 8 planets orbit our sun, each one different, each one strange in its own way, and each one hiding questions we're still trying to answer. Jupiter is massive, more than twice as heavy as all other planets combined. If you could see below those swirling clouds, what would you find? We don't know. Jupiter is mostly hydrogen and helium, like a star that never got big enough to ignite. The pressure increases as you go down. Eventually, the pressure gets so high that hydrogen stops acting like gas and starts acting like metal. Metallic hydrogen, a substance we can barely create in labs on Earth. Below that might be a rocky core, maybe 10 times Earth's mass. Or maybe not. Maybe Jupiter has no solid surface at all, just layers of fluid getting denser and denser until you reach the center. The Great Red Spot has been spinning on Jupiter for at least 200 years. It's a storm bigger than Earth. Winds there reach 400 miles per hour, but it's shrinking. 100 years ago, it was twice as wide as it is now. We don't know why it's shrinking, or if it will eventually disappear. Europa, one of Jupiter's moons, has ice covering its surface. But underneath that ice sits an ocean of liquid water. We know this from the way Jupiter's gravity flexes Europa, heating its interior. That ocean might be twice as deep as all of Earth's oceans combined. Does life exist there? In the darkness beneath the ice, warmed by tidal heating, with possible hydrothermal vents on the HUD. Ocean floor? We don't know. But Europa is one of the best places in our solar system to look. We're planning missions to drill through the ice and sample the water. The answer might be waiting. Saturn has rings made of ice and rock. Billions of pieces ranging from dust specks to house-sized boulders. They're beautiful. They're temporary. The rings are only about 100 million years old, young compared to Saturn's 4.5 billion year age. And they're falling into Saturn, raining down as icy particles. In another 100 million years, they might be gone. Why does Saturn have rings when Jupiter barely does? Why are Saturn's rings so bright and detailed? We think they came from a moon that got too close and broke apart, but we're not certain. Enceladus, another moon of Saturn, shoots geysers of water into space from cracks at its south pole. This water comes from an ocean beneath the ice, just like Europa, and in that water we've detected organic molecules, the building blocks of life. Not life itself, but ingredients that could lead to it. Venus is almost Earth's twin in size, but it's hell. The surface temperature is hot enough to melt lead. The atmosphere is thick carbon dioxide with clouds of sulfuric acid. The pressure at the surface is like being a mile underwater. Why is Venus so different from Earth? Both planets started similar, but Venus is closer to the Sun. It got a bit warmer. That warmth let more water evaporate. Water vapor is a greenhouse gas. It trapped more heat, which caused more evaporation. This runaway greenhouse effect boiled away Venus's oceans and turned it into an oven. But here's what we don't know. Did Venus ever have oceans? Did it ever have life? Could it have been like Earth billions of years ago before everything went wrong? The surface is too hot to preserve any evidence. The rocks have been recycled many times. Venus's past is erased. Mars had water once. Rivers carved channels across its surface. Lakes filled craters. Maybe even an ocean covered its northern hemisphere. But that water disappeared. Mars lost its atmosphere over billions of years. Solar wind stripped it away after Mars's magnetic field died. Without air pressure, the water evaporated or froze into the ground. Where exactly did it all go? Some is in the polar ice caps. Some is trapped as ice below the surface. But we haven't found it all yet. Uranus spins on its side. Its axis is tilted 98 degrees. All the other planets spin roughly upright, like tops. But Uranus rolls along its orbit like a ball. Something must have hit it long ago, knocking it over. But what? And when? We don't know. These worlds in our solar system are places we can visit with robots. Places we can study. But they're just a few planets around one star. And beyond them lies something that makes up most of the universe. Everything you can see, every star and planet and galaxy, makes up less than 5% of the universe. The rest is invisible. And most of that invisible part is something we call dark matter. We can't see it, can't touch it, can't detect it directly with any instrument. So, how do we know it exists? Galaxies spin. Our Milky Way rotates once every 200 million years. And when scientists measured how fast stars at the edge of galaxies move, they found something wrong. Those stars were moving too fast, way too fast. Think of it like a merry-go-round. If you spin it faster and faster, eventually people on the edge fly off. Gravity from the center isn't strong enough to hold them. Galaxies should work the same way. The visible matter, all the stars and gas we can see, doesn't have enough gravity to hold the outer stars in place at the speeds they're moving. But the stars don't fly away. Something invisible is holding them. Something with gravity. Something with mass. We call it dark matter. It's everywhere. There's about 5 times more dark matter than normal matter in the universe. It forms a scaffolding that galaxies grow around. A cosmic web of invisible threads connecting everything. Light bends when it passes near massive objects. Einstein predicted this. We've confirmed it. And when we look at distant galaxies, we see their light bending around clusters of galaxies in front of them. The bending is too strong for the visible matter alone. Dark matter is there, warping space with its gravity, even though we can't see it. So, what is it made of? Nobody knows. That's the honest answer. It's not normal atoms, not protons, neutrons, and electrons. Those would interact with light. We'd be able to see them. Dark matter passes through normal matter like it's not even there. It only interacts through gravity. Maybe it's made of particles we haven't discovered yet. Theoretical particles with names like WIMPs, weakly interacting massive particles, or axions, or sterile neutrinos. Scientists have built detectors deep underground, shielded from cosmic rays, waiting for a dark matter particle to bump into normal matter. So far, nothing. The particles, if they exist, are even more elusive than we thought. Could we be wrong about dark matter? Could our understanding of gravity be incomplete instead? Maybe gravity works differently at the scale of galaxies. Maybe it's stronger at large distances than we think. Some scientists explore this idea. They call it modified gravity. But it has problems. It doesn't explain everything. Dark matter explains. The evidence keeps pointing back to invisible matter. Where is dark matter densest? We think it clumps in halos around galaxies. It should be passing through Earth right now. Millions of dark matter particles flowing through your body every second. You don't feel them. They don't interact with you. They pass through like you're not here. Is dark matter one thing or many? Maybe there are different types of dark matter particles, just like there are different types of normal particles. Maybe dark matter has its own complex physics, its own forces and interactions we can't see. An entire dark sector of physics operating alongside the world we know. We're searching, building better detectors, looking at space in new ways, trying to catch a glimpse of what makes up most of the matter in the universe. And dark matter isn't even the strangest thing out there. There's something else, something even more mysterious, something that's pushing the universe apart. The universe is expanding. Every galaxy is moving away from every other galaxy. Space itself is stretching, and it's not just expanding. It's accelerating, getting faster. This shouldn't happen. Gravity should slow expansion down. After the Big Bang, everything flew outward, but gravity pulls everything back together. The expansion should be slowing. Eventually, maybe even reversing. The universe should be decelerating. Instead, it's speeding up, and we don't know why. We call the cause dark energy, but that name is just a placeholder for our ignorance. We have no idea what it actually is. In 1998, 2 teams of astronomers were measuring distant supernovas. These exploding stars are useful because they all have roughly the same brightness. By measuring how dim they appear from Earth, you can figure out how far away they are. Both teams found the same shocking result. Distant supernovas were dimmer than expected. They were farther away than they should be. The universe had expanded more than predicted, and this meant something was pushing galaxies apart. Some force opposing gravity, some energy filling empty space. Dark energy makes up about 70% of everything in the universe. It's the dominant component, yet we can barely describe what it does, let alone what it is. One idea is that empty space has energy built into it. Quantum mechanics says even a vacuum isn't truly empty. Particles pop into and out of existence constantly. These quantum fluctuations might create a kind of pressure, a negative pressure that pushes space apart instead of pulling it together. But when physicists calculate how much vacuum energy there should be, they get a number that's way too big, off by a factor of 10 to the power of 120. That's one with 120 zeros after it. It's possibly the worst prediction in the history of physics. So, vacuum energy might not be the answer. Or maybe something cancels most of it out, leaving just enough to cause the acceleration we see. Is dark energy constant? Does it have the same strength everywhere and always? Or could it change over time? Could it vary from place to place? Right now, our observations fit with dark energy being constant, but we can't rule out the possibility that it evolves. This matters for the future of the universe. If dark energy stays constant, galaxies will drift apart forever. In trillions of years, each galaxy will be alone in an expanding void. Stars will burn out. Black holes will evaporate. Everything will go dark and cold. But if dark energy strengthens over time, something more dramatic could happen. It could tear apart galaxies, then solar systems, then planets, then atoms themselves. Scientists call this the Big Rip. Space would expand so fast that nothing could hold together anymore. If dark energy weakens, gravity might win eventually. The universe could stop expanding and start contracting. Everything could collapse back together in a big crunch. We don't know which future awaits. We can only measure what dark energy is doing now and make predictions. What does it mean for there to be an energy in empty space? What does it mean for space itself to have properties? These questions take us back to the beginning, to the moment when space and time and everything in them came into existence. The moment of the Big Bang. 13.8 billion years ago, everything began. Not just matter and energy, not just galaxies and stars. Space itself, time itself, everything. We call it the Big Bang. But that name is misleading. It wasn't an explosion in space. It was an expansion of space. Space itself started incredibly small, maybe infinitely small, and grew. And it's still growing. But what caused it? What came before? These might be the deepest questions we can ask. And we don't have answers. In the first fraction of a second, the universe was unimaginably hot and dense. Hotter than the center of any star. So hot that particles couldn't form. Just pure energy filling everything. Then it cooled, just a bit, and particles appeared. Quarks, electrons, photons. The universe was about a millionth of a second old. After 3 minutes, it cooled enough for protons and neutrons to stick together. Hydrogen nuclei formed. Helium nuclei formed. The first atomic nuclei in the universe. But it was still too hot for electrons to attach. The universe was a glowing plasma, opaque to light. After 380,000 years, it cooled enough for electrons to attach to nuclei. Atoms formed. The universe became transparent. Light could travel freely for the first time. That light is still traveling. We see it today as the cosmic microwave background, the faint glow of the early universe coming from every direction in space. But here's what we don't understand. Why is there something instead of nothing? Physics says that for every particle of matter, there should be a particle of antimatter. Matter and antimatter annihilate when they meet, turning into pure energy. So, in the early universe, matter and antimatter should have destroyed each other completely. Everything should have turned into light. There should be no matter left, no atoms, no stars, no us. But we're here. Somehow, there was slightly more matter than antimatter. About 1 extra matter particle for every billion pairs. That tiny imbalance is everything. All the matter in the universe today came from that small excess. Why? What caused the asymmetry? We don't know. Something violated the perfect symmetry between matter and antimatter. Some process in the first moments of the universe created more of one than the other. We're looking for it, testing theories, but we haven't found the answer. And what set the laws of physics? Why does gravity have the strength it has? Why are there 4 fundamental forces instead of 3 or 5? Why do electrons have the mass they have? These values seem arbitrary. But if they were even slightly different, the universe would be completely different. Stars might not form. Atoms might not be stable. Life would be impossible. Some scientists think our universe is one of many, a multiverse where different universes have different laws. We happen to be in one where the laws allow life to exist. We're here because we have to be here. We couldn't observe a universe that couldn't create observers. But that's speculation. We can't test it. We can only observe our universe. What came before the Big Bang? Maybe nothing. Maybe time itself started with the Big Bang. So, asking what came before is like asking what's north of the North Pole. The question doesn't make sense. Or maybe our universe came from another universe. Maybe universes branch off from black holes. Maybe they cycle, expanding and contracting forever. Maybe the Big Bang was a bounce, a previous universe collapsing and rebirthing as ours. These ideas push at the edges of physics. They take us into territory where the very small meets the very large, where quantum mechanics meets the structure of space and time. At the smallest scales, reality gets strange. The rules that govern everyday objects stop working. New rules take over. Rules that seem impossible. Rules that challenge everything we think we know about how the world works. This is the quantum realm, and it's full of mysteries. Take light. Is it a wave or a particle? The answer is both, and neither. Light behaves like a wave. When it travels through space, it ripples, it interferes with itself, it bends around corners. But when light hits something, when it gets absorbed or emitted, it acts like a particle, a discrete packet of energy called a photon. The same is true for electrons, for atoms, for everything at small enough scales. They're waves and particles at the same time. We call it wave-particle duality, but we don't really understand what it means. When you're not looking at an electron, it doesn't have a definite position. It's spread out. It exists in many places at once, as a wave of probability. Only when you measure it does it become real in one specific location. The act of observation changes reality. How does that work? How does the universe know when you're looking? What counts as an observation? These questions have puzzled physicists for almost 100 years. Then there's quantum entanglement. Take 2 particles and interact them in certain ways. They become connected, entangled. Now measure 1 particle. Instantly, you know something about the other particle, even if it's on the other side of the universe. The measurement of one affects the state of the other faster than light could travel between them. Einstein called this spooky action at a distance. He didn't like it. He thought it meant quantum mechanics was incomplete, that there must be hidden variables we weren't seeing. But experiments have proven entanglement is real. The connection between entangled particles is immediate. Information doesn't travel between them. They're not sending signals. They just share a state that can't be described separately. We use entanglement in quantum computers. We can measure it, but we can't fully explain it. What causes quantum collapse? Before you measure a quantum system, it exists in superposition. Multiple states at once. An electron can be spinning up and spinning down simultaneously. But when you measure it, you get one answer. The superposition collapses into a single state. Why? What triggers the collapse? Is it consciousness? Is it interaction with any large object? Is it something about the measuring device? Different interpretations of quantum mechanics give different answers, and we can't tell which is right. Some interpretations say the universe splits every time a quantum measurement happens. One version of you sees spin up, another version sees spin down. Both are real, just in different parallel universes. We live in a constantly branching multiverse of every possible quantum outcome. Other interpretations say the wave function, the mathematical description of quantum possibilities, is all that exists. It never collapses. It just looks like it collapses to us because we're part of the wave function too. Is reality real? Do things have definite properties before we measure them? Quantum mechanics says maybe not. Maybe reality is fundamentally probabilistic. Maybe the universe doesn't decide what's real until it has to. What is quantum foam? At scales smaller than an atom, smaller than a nucleus, smaller than anything we can directly see. Space and time might not be smooth. They might fluctuate wildly. Virtual particles might pop in and out of existence. The fabric of reality might be bubbling and churning like foam. These quantum mysteries touch everything. They affect how atoms bond, how particles decay, how the universe evolved in its first moments. And they connect to something we experience every day but can't explain. Time itself. You're moving through time right now. 1 second per second. Always forward, never back. It feels natural, inevitable. But time is stranger than it seems. What is time made of? Is it a thing that exists, like space? Or is it just a way our brains organize change? Physics treats time as a dimension, like length or width or height. You can move through space in any direction, but you can only move through time in one direction. Why? We call it the arrow of time. The past is fixed. The future is open. You remember yesterday, but not tomorrow. Eggs break, but don't unbreak. Coffee cools, but doesn't spontaneously heat up. Time has a direction, but the fundamental laws of physics don't. Most equations in physics work the same forward or backward in time. If you filmed particles bouncing off each other and played the video in reverse, the reversed motion would still obey the laws of physics. The equations don't care which way time flows. Yet, we experience a clear direction. Why? Entropy. That's the usual answer. Entropy is a measure of disorder. The second law of thermodynamics says entropy always increases. Things naturally go from ordered to disordered. A messy room doesn't clean itself. A shattered cup doesn't reassemble. The universe is running down from order to chaos. And that gives time its arrow. We call the past the direction of lower entropy. The future is the direction of higher entropy. But this just moves the mystery. Why was entropy low in the past? Why did the universe start in such an ordered state. The Big Bang created a universe with very low entropy. All the matter and energy were smooth and evenly distributed. That's actually a very special, unlikely state. Since then, gravity has clumped matter into stars and galaxies and black holes, increasing entropy. But why did it start that way? We don't know. Is time travel possible? Einstein's equations allow it under certain conditions. If you could create a wormhole, a tunnel through space and time, you might be able to travel to the past. If you could spin a cylinder of matter fast enough, space and time around it would twist in ways that might let you loop back. But every time scientists find a solution that allows time travel, they also find problems. Paradoxes. If you travel back and prevent your own birth, what happens? Do you cease to exist? Does the universe split into timelines? Do the laws of physics prevent you from doing it somehow? Some physicists think time travel to the past is impossible in principle. Maybe quantum mechanics forbids it. Maybe causality, the rule that causes come before effects, is more fundamental than the equations suggest. Does time exist? Some physicists think time is an illusion, that the universe is really a four-dimensional block where past, present, and future all exist equally. We experience time flowing because our consciousness moves through this block, moment by moment. But the block itself is timeless. Everything that ever happened or will happen already exists. Others think time is fundamental, that becoming, the creation of new moments, is real, that the future doesn't exist yet. What is now? Your brain takes time to process information. By the time you're aware of something, it already happened. Different parts of the universe experience time at different rates, depending on gravity and motion. There's no universal now that everyone shares. Time bends. Near massive objects, time slows down. Time and space are connected, woven together into space-time. A fabric that can curve and stretch and ripple. Space and time aren't separate things. They're connected, woven together into a fabric called space-time. And that fabric bends. This is gravity. Not a force pulling things together, but a curve in space-time itself. Mass tells space-time how to curve. Space-time tells mass how to move. Imagine a stretched rubber sheet. Put a bowling ball on it. The sheet dips. Now roll a marble past the bowling ball. The marble curves toward it, following the dip in the sheet. That's how gravity works. Earth curves space around it. You follow that curve. That's why you fall. Einstein figured this out over 100 years ago. His equations predicted things we later confirmed. Light bends around massive objects. Time runs slower in stronger gravity. Gravitational waves ripple through space when massive objects collide. In 2015, we detected gravitational waves for the first time. Two black holes, each about 30 times the mass of the Sun, spiraled into each other and merged. The collision sent ripples through space-time that reached Earth a billion years later. Detectors measured the stretching and squeezing of space itself. The change was tiny, smaller than the width of a proton. But we caught it. Since then, we've detected dozens more gravitational wave events. Black holes merging, neutron stars colliding. Each one teaches us something new about how gravity works in extreme conditions. But here's what we still don't understand. What is gravity exactly? We can describe how it behaves. We can predict what it does. But we don't know what it fundamentally is. The other forces of nature, electromagnetism and the nuclear forces, are carried by particles. Photons carry electromagnetic force. Gluons carry the strong nuclear force. W and Z bosons carry the weak nuclear force. Gravity should work the same way. There should be a particle called the graviton that carries gravitational force. But we've never detected one, and trying to build a quantum theory of gravity leads to mathematical problems, infinities that don't make sense, predictions that break down. Gravity is the odd one out. It doesn't fit with quantum mechanics, and unifying them, creating a theory of quantum gravity, is one of the biggest unsolved problems in physics. Do gravitational waves tell us everything? They're opening a new window on the universe. We can detect events we could never see with light. Black holes have no light to emit. Neutron-star collisions happen too fast for traditional telescopes to catch the beginning. But gravitational waves let us observe these events directly. Still, gravitational waves only carry certain information. They tell us about mass and spin and distance. But they don't tell us everything about what's happening inside extreme objects. They don't reveal what matter does under the most intense conditions. Some mysteries remain hidden even from gravitational wave detectors. What happens inside black holes? Cross the event horizon, the boundary of a black hole, and you can't escape. Light can't escape. Nothing can. All paths through space-time lead inward. At the center sits something called a singularity, where density becomes infinite and the equations of physics break down. But does the singularity really exist? Or does something else happen that we can't calculate? Maybe quantum effects matter at that scale. Maybe there's no true singularity, just matter compressed to scales where our current theories stop working. What is space-time made of? Is it continuous, smooth, all the way down? Or is it discrete, made of tiny units too small to measure? Some theories suggest space-time has a smallest possible scale, a quantum of space about 10 to the power of minus 35 meters across. Below that scale, the concept of distance stops making sense. These questions take us to the most extreme places in the universe. Places where gravity becomes so strong that even light can't escape. Black holes are where gravity wins completely, where space curves so sharply that nothing can climb back out. Not light, not matter, not information. Once something crosses the event horizon, it's gone from our universe. At least, that's what we thought. Stephen Hawking showed that black holes aren't completely black. Quantum effects near the event horizon create pairs of particles. One falls in, one escapes. To an outside observer, the black hole radiates. It glows with what we call Hawking radiation. And over incredibly long times, trillions upon trillions of years, this radiation would cause a black hole to evaporate completely. But this creates a paradox. Quantum mechanics says information can't be destroyed. Everything that falls into a black hole carries information. Its quantum state, its history, If the black hole evaporates, where does that information go? Does it come back out in the Hawking radiation, scrambled but preserved? Or does it vanish, breaking the rules of quantum mechanics? We don't know. The black hole information paradox has troubled physicists for decades. Some think information is preserved in ways we don't understand yet. Others think maybe information can be destroyed, and we need to rethink quantum mechanics. The answer requires understanding both quantum mechanics and gravity together, something we can't fully do yet. What's at the center of a black hole? The equations say a singularity, a point of infinite density. But infinity usually means the equations are breaking down, not describing reality. At those scales, quantum effects should matter. Space and time themselves might dissolve into something else. Some theories suggest the center contains a region of highly compressed matter, not a true singularity. Others think it might connect to another region of space-time, maybe even another universe. We can't observe it. We can only speculate. How do supermassive black holes form? At the center of most galaxies sits a black hole, millions or billions of times the mass of the Sun. Our Milky Way has one, about 4 million solar masses. Some galaxies have black holes billions of times heavier. These monsters formed early in the universe's history. We see them when the universe was less than 1 billion years old. But we don't know how they got so big so fast. Black holes grow by eating matter and by merging with other black holes. But doing this in the time available seems difficult. They might have formed from enormous clouds of gas collapsing directly, skipping the star stage entirely. Or maybe they grew from seeds created by the first generation of stars. We're still figuring it out. What is a white hole? In theory, they're the opposite of black holes. Instead of matter falling in forever, matter erupts out forever. Nothing can enter. Everything escapes. Einstein's equations allow white holes to exist, but we've never seen one. They might not be stable, or they might not exist at all. They're mathematical possibilities more than physical realities. What are quasars? They're the brightest objects in the universe. A single quasar can outshine an entire galaxy. They're powered by supermassive black holes actively feeding on matter. Gas and dust spiral into the black hole, heating up to millions of degrees and emitting enormous amounts of light before crossing the event horizon. We see quasars from the early universe. They were more common then, when galaxies were still forming and merging, feeding black holes more actively. Today, most supermassive black holes are quiet, including the one at the center of our galaxy. They've consumed most of the nearby matter. They sit dormant, waiting. These cosmic giants sit in galaxies, and galaxies themselves form patterns across space. Galaxies aren't scattered randomly through space. They form patterns, clusters, superclusters, long filaments stretching across hundreds of millions of light years. And between these filaments lie voids, vast, empty regions with almost nothing in them. This is the cosmic web, the largest structure in the universe, and we're still learning how it formed. Dark matter created the scaffolding. In the early universe, dark matter clumped together under its own gravity. Normal matter fell into these clumps. Gas cooled and condensed. Stars formed. Galaxies took shape. But the details remain unclear. How do galaxies actually form? We see them at all stages. Young galaxies in the early universe, messy and irregular. Mature galaxies like ours, with organized spiral arms or smooth elliptical shapes. Old galaxies where star formation has stopped, filled with ancient red stars. The transition from gas cloud to galaxy involves complex physics. Star formation, supernova explosions pushing gas around, black holes at galaxy centers affecting their surroundings, galaxies merging and pulling each other apart. Computer simulations can reproduce some of these processes, but matching the simulations to what we observe requires tweaking. We're still refining our understanding. Why do galaxies have different shapes? Spiral galaxies, like the Milky Way, have flat disks with arms. Elliptical galaxies are round or oval, with no distinct structure. Irregular galaxies have no clear shape at all. Shape seems to depend on history. Galaxies that formed smoothly and haven't collided much stay spiral. Galaxies that merged with others get stirred up, becoming elliptical. But not all details fit this picture. Some galaxies have features we can't fully explain. Rings, bars, streams of stars stretching into space. There's something pulling us, not just Earth, not just the Milky Way. Our entire local group of galaxies, dozens of them, is moving in one direction at about 1 million miles per hour. Something massive is attracting us. We call it the Great Attractor. It's a region of space about 200 million light-years away. Tens of thousands of galaxies cluster there. Their combined gravity is pulling everything nearby toward them. But we can't see it directly. It's hidden behind the plane of our own galaxy, obscured by dust and stars. And beyond the Great Attractor, there might be something even bigger, an even larger concentration of matter pulling on the Great Attractor. We're mapping these structures, trying to understand the full picture of what's moving what. Are we alone in the universe? This might be the question that matters most. Is life common or rare? Does intelligence arise often or almost never? We've found no evidence of other life yet. No alien signals. No signs of technology. No biosignatures in the atmospheres of distant planets. But we've barely started looking. We've only carefully studied a tiny fraction of the stars in our galaxy. And there are hundreds of billions of galaxies beyond ours. How many galaxies exist? We can see about 200 billion galaxies with current telescopes. But that's just in the observable universe, the part we can see. Space extends beyond what light has had time to reach us. There might be infinitely many galaxies out there, forever beyond our view. What's beyond the observable universe? We can't know. Light from farther away hasn't reached us yet. It might never reach us if space expands fast enough. There could be other galaxies, other clusters, other structures. Or the universe might end. Or it might loop back on itself. We can only observe our cosmic bubble, about 93 billion light-years across. Everything beyond that is speculation. But within what we can see, we keep searching. Searching for the answer to one question above all others. In all the universe, as far as we know, life exists in one place. Here, on this small blue planet orbiting an ordinary star. But that seems unlikely. With hundreds of billions of stars in our galaxy alone, and hundreds of billions of galaxies beyond, the numbers suggest we shouldn't be alone. Yet, we haven't found anyone else. This is the Fermi paradox. If intelligent life is common, where is everybody? Why haven't we heard from them? Why don't we see signs of their technology? Space is old, 13.8 billion years old. Life on Earth is only about 4 billion years old. If life arose on a planet just a billion years earlier than ours, that civilization would have had a huge head start. They could have spread across the galaxy by now. We should see them, but we don't. Maybe intelligent life is rare. Maybe the steps from simple chemicals to living cells to complex organisms to intelligence are incredibly unlikely. Maybe we're the first, or one of the first, to reach this point. Maybe intelligent life is common, but technological civilizations don't last long. Maybe they destroy themselves. Wars, environmental collapse, technologies they can't control. Maybe the window between developing radio signals and going extinct is just too short. Maybe they're out there, but staying quiet. Maybe making noise in space is dangerous. Maybe civilizations that broadcast their presence attract attention they don't want. So, everyone is listening, but nobody is talking. Or maybe we're looking in the wrong way. We're searching for radio signals, assuming aliens would use technology like ours. But a civilization a million years ahead of us might communicate in ways we can't imagine. Or they might have moved beyond physical form entirely. How do we define alien life? We look for life like ours, carbon-based, using water, needing similar temperatures. But life might be more flexible than we think. It might use different chemistry, silicon instead of carbon, ammonia instead of water. It might thrive in conditions that would destroy Earth life. On Saturn's moon, Titan, lakes of liquid methane cover the surface. The temperature is negative 290 degrees. Water is rock hard, but methane is liquid. Could life use methane the way we use water? Could there be organisms swimming in those cold lakes using different chemistry entirely? Where should we look? We're finding planets around other stars constantly. Thousands of them. Some are rocky like Earth. Some orbit in the habitable zone where temperatures allow liquid water. These are our best candidates. We're building bigger telescopes. We're analyzing the atmospheres of distant planets, looking for gases that don't belong. Oxygen, methane, combinations that only make sense if something is producing them. Something alive. What would aliens be like? Science fiction shows us humanoids, creatures we can relate to, but real aliens might be nothing like us. They might be microscopic. They might be vast, slow-thinking organisms the size of continents. They might be artificial intelligences, the descendants of biological life that uploaded itself into machines. If we found a signal from aliens, could we understand it? Their mathematics might be similar to ours. Math is universal, but their concepts, their culture, their way of thinking might be so different that communication is impossible. We might recognize intelligence without being able to comprehend it. And maybe the question, isn't whether aliens exist. Maybe it's whether we'll find them before we destroy ourselves, whether we'll last long enough to make contact, whether we'll become the ancient civilization that others find evidence of, or whether we'll be here to greet them. These questions about life beyond Earth lead back to questions about ourselves. We started this journey with questions close to home. What is consciousness? Why do we dream? Mysteries inside your own mind. Then we moved outward, through your body, through Mad's origin, through evolution and Earth, and the oceans and the sky. We traveled to the sun, to distant planets, to invisible dark matter and mysterious dark energy. Back to the beginning of everything, down to the quantum realm where reality itself becomes uncertain, through time and space and gravity, to black holes and galaxies and the cosmic web stretching across the universe. And finally, to the question that connects it all. Are we alone? 100 questions. Some we might answer soon. Some might take centuries. Some might be unanswerable. Mysteries that push against the limits of what minds like ours can understand. But here's what all these questions share. They remind us how much we don't know, how vast the unknown still is. And that's not something to fear, it's something to celebrate. Science isn't about having all the answers. It's about asking better questions, about being comfortable with uncertainty, about looking at the universe with wonder and saying, I don't know yet, but I want to find out. You're part of this search. Every time you look up at the stars and wonder what's out there. Every time you notice something strange in nature and ask why. Every time you learn something new about how the world works. You're participating in the greatest adventure humans have ever undertaken. The journey to understand everything. And the beautiful part, we'll never finish. Every answer leads to new questions. Every discovery opens new mysteries. The universe seems designed to keep us curious forever. So, as you drift towards sleep tonight, remember this. You live in a universe that's mostly invisible, made of things we can barely detect, expanding into nothing, running on rules we're still figuring out. You're made of atoms forged in dying stars. You're conscious for reasons we don't understand. You dream in ways we can't explain. You're a mystery experiencing mysteries. And that's wonderful. What questions will we answer next? What will we discover tomorrow, or next year, or in the next century? What mysteries are waiting that we haven't even thought to ask about yet? Nobody knows. And that's the point. The unknown isn't empty. It's full. Full of possibilities. Full of wonders waiting to be found. Full of questions that will keep humans curious for as long as we exist. If these quiet explorations bring you peace, if you've enjoyed this journey through the mysteries of science, consider subscribing. There are more mysteries waiting, more questions to explore, more wonder to discover together. And leave a comment. Tell us which question resonated with you most, which mystery you hope we solve first, where you are in the world as you listen to this, what time it is there. We love knowing there are people out there, in different places, different time zones, all wondering together. Tomorrow brings new mysteries, new questions, new chances to explore the unknown. The universe will still be here in the morning, still mysterious, still waiting, still full of questions. And you'll be here too, still curious, still wondering, still part of this beautiful ongoing search for understanding. Sleep well, dream of mysteries, and wake ready to wonder again.